Namaste and warm welcome to all of you. In the last lecture by Dr. Ashok Rao, you would have studied the idea of singular value decomposition. We said that look, we were trying to do a kind of decomposition of rectangular matrices. I mean, which eventually turns out that you can do it even for square matrices. Like what we did with eigenvalues and eigenvectors in case of a square matrix. We wanted to see if we can decompose a rectangle matrix similar to what we did with square matrices, where in which we said A is equal to PDP inverse. So that was what we were looking at, and we in fact found, Dr. Ashok Rao taught you that yes, in fact we can do this kind of a decomposition of a rectangular matrix as U sigma V transpose. So the significant difference that you would see in both the cases is that in case of square matrices which were diagonalizable, it was the same matrix P which was used to diagonalize the matrix A as A D is equal to P inverse AP. But in this case of singular value decomposition, which we did with let us say our U sigma V transpose for a rectangular matrix, we were not able to diagonalize it using a single matrix P. Instead, what we do is we took two matrices U and V, and we said that fine, if I cannot get one matrix P which would diagonalize, I would choose two matrices, let us say U and V, which would help me diagonalize the matrix A. Now, if you recall, when we did real symmetric matrices, we had a question. We said, look, when we looked at the transformation A acting on the vector x, we wanted to actually find out what is this matrix A doing to that vector x, and we appreciated the effect of the matrix A on the vector x when A was a real symmetric matrix with distinct eigenvalues. So what did we do there? We said that if A was a real symmetric matrix, let we will say this, let A be a real symmetric matrix with distinct eigenvalues. Now, we already knew the property of the real symmetric matrices with distinct eigenvalues is that the eigenvectors corresponding to the distinct eigenvalues were orthogonal to each other, right. So, let A be a real symmetric matrix with distinct eigenvalues. Distinct eigenvalues. Let us say I will just take a simple example where I will take A to be a 2 by 2 matrix. You can take it for any n by n matrix with distinct eigenvalues, means you will get n distinct eigenvalues with distinct so here I am just going to consider a very generic case of A, very simple case of A is equal to A is a 2 by 2 matrix. Then we say that then we know that the eigenvectors corresponding to distinct eigenvalues are orthogonal to each other. Distinct eigenvalues, let us say in this case let us make it as lambda 1 and lambda 2, okay, and lambda 1 not equal to lambda 2 because they are distinct. So, distinct eigenvalues are orthogonal to each other. Right, this is what we had, and when we had this result, we understood the effect of A. That means we wanted to find out what does A do, what does A do to the vector x to give us a B, to give the vector B, right. And we know that if you recollect very clearly, we had this Ax and we said this is nothing but lambda 1. Let us assume that associated with lambda 1 is the eigenvector u and associated with the lambda 2 eigenvalue is the eigenvector v. So, we said that Ax is nothing but lambda 1 u transpose plus lambda 2 v transpose into x. Basically we said that this is going to be lambda 1 u transpose x into u plus lambda 2 v transpose x into v, and we also said that in this case the u and v, the vectors u and v are orthonormal vectors. That means you have already made them to be length 1. So, we said that they are orthonormal vectors, and what we did was we said that look, the effect of this matrix A on the vector x is basically project the vector x onto two orthogonal axes, the orthogonal axis being the vector u and the vector v, and scale those projections, and that is exactly what we had here. This is basically, I can write this as, if you look at this equation 1, I can write this equation 1 as Ax is equal to lambda 1 u transpose x by u transpose u, because they are orthonormal, u transpose u will be 1 in the direction of u becomes a unit vector now, plus lambda 2 v transpose x divided by v transpose v in the direction of v is also a unit vector. So, we say that look, the effect of A on the real symmetric matrix A with distinct eigenvalues on the vector x is basically to project those two vectors onto the eigen directions which are orthogonal and then scale those projections. Now, I ask the same question, like I have done this when we come to our singular value decomposition. I again ask this question, like can we get an interpretation something like that, where we had let us say A m by n real matrix and we had x which is an n component vector, I end up getting a vector b m by 1, right. So, basically I have the x to be a vector from Rn and b to be a vector in Rm. So, this is exactly where the transformation happens, the linear transformation. In the other case, A, the real symmetric matrix case, A was actually an operator which was taking you from which was taking a vector from Rn and then putting it back to Rn itself, whereas in this case you are going to have a totally two different structures here. One is Rn, the other structure is Rm, two different vector spaces. So, I want to ask this question, what does A do to the vector x to get you a b, right? The question is, how do we get this Ax equal to b? What is the effect of A on x? What happens geometrically to give me this b vector? That is a valid question, because that is a question that we had asked previously in case of real symmetric matrix 2. So, how do we understand this? How does A, for example, I take this, let us say I have 2 1 1 2, then let me take 1 1 is going to, let us say it is going to take any vector x1 x2, basically this vector is in Rn, I mean R2, and I am going to get a vector which is in R3 which is nothing but 2 x1 plus x2, x1 plus 2 x2, and I have x1 plus x2. This is what I have. Mathematically I can see that, look, I am just multiplying a couple of numbers and then adding those numbers. I am doing it for 3 times with 3 different set of numbers and I get a vector b. So, this is A and that fellow is x and that fellow is b. But geometrically what happens? So, the question still remains, what happens geometrically? And to answer this question, what we do is we look at single value decomposition. This is precisely what Professor Ashokra was also saying. He said that, look, the matrix, what does it do? The moment you say A into V, what happens is that fellow is going to take you to another vector u which is going to be there in the column space of the matrix A, and then something happens. So, what are we going to do? You recall our SVD for recall. the SVD of any real of a matrix A is given by A is equal to U sigma V transpose. This is what we had, and what was A was basically an m by n matrix, which was basically U m by m matrix. We had the sigma matrix, which was basically m by n, and V transpose was basically n by n, right. We had this. So, let us understand what is this U, V and sigma, what are these fellows, we will understand what they are. If you look at V is basically the V matrix contains vectors which are contains orthonormal eigenvectors of A transpose A. U matrix contains orthonormal vectors eigenvectors of A transpose, and the matrix sigma is going to contain the singular values. Of course, the singular values are arranged in decreasing order, and accordingly the vectors are also populated in the matrix U and V, singular vectors. Now, if you go back to our eigenvalue case, here we have A is equal to, it is basically P D P transpose. This is what we had. If A is a real symmetric matrix with distinct eigenvalues, right. If you compare this expression A is equal to P D P transpose with A is equal to U sigma V transpose, we see some striking similarity here. In both the cases, the right extreme matrix that you have is basically the transpose matrix, and the middle matrix is basically a diagonal matrix, though in this rectangular case it is not perfectly diagonal. You can find a diagonal submatrix out there, and U is another orthonormal matrix that we have. Now, if you compare to the original the actual eigen decomposition of any matrix A, that is going to be given by PD P inverse. This is for any diagonalizable matrix A, right. This is what we have. Now, if you compare again these this expression with this expression, we see P transpose plays the role of P inverse, and when will a matrix have its inverse to be its transpose? We very clearly know whenever the matrix is orthogonal matrix, that means the columns of the matrix are orthogonal to each other and each column vector is of unit length, we know that the inverse of the matrix is the transpose, and that is exactly what we have here. P, in this case, if you look at it, the matrix P has orthogonal eigenvectors, and the eigenvectors were also normal. That is what we said, U transpose U, V transpose V is 1. So, we naturally get P inverse to be equal to P transpose. If you compare that with this U sigma V transpose acts like the P inverse, but just that you have V transpose is equal to this, V transpose does the operation of this inverse. Quite naturally, because you see that V contains orthonormal eigenvectors, that means V is an orthogonal matrix, therefore the inverse will be transpose itself. And sigma is exactly what you see in the case of our eigen decomposition, except that in that case it is a diagonal matrix, here it is a rectangular matrix which is a submatrix which is diagonal, and U is also an orthogonal matrix with orthonormal columns. So, now I could easily compare these two. So, if I write Ax equal to B, it simply means I have Ax, which is nothing but U sigma V transpose x, which is equal to B. Oh, that's pretty interesting again. Why? Because I have already got an expression which is similar to what I had seen in the case of diagonalization of a real symmetric matrix with distinct eigenvalues. I have Ax is equal to U sigma V transpose X, and that's equal to B. Now it's easy for me to figure out what is this matrix A doing to that vector X to get to the vector B. So what is the transformation A actually doing? And if you see it, V transpose X, this we will, I mean we will say that this is going to perform the rotation of the vector X. Rotation, since it's an orthonormal matrix, the V transpose X is going to preserve the length of the vector, because the determinant of V transpose is going to be 1, because the columns are all 1. So the determinant is going to be 1. So V transpose X in effect is going to rotate the vector X, and then what it's going to do is that rotated vector is going to get scaled. The point here is the scaling is going to be uneven scaling here, uneven scaling in the sense you are going to have sigma 1, sigma 2, sigma r, where r corresponds to the rank of the matrix. Each of those directions are going to get scaled in a different way, and then what happens, you are going to have the resultant vector which is also going to be multiplied by u, which is going to act as another rotation. So what we are going to do is we are just going to say that the effect of the matrix A on a vector X is basically to rotate a vector, scale them, and then rotate again. So what happens, we will understand it through what we call as the action ellipse and stuff. So we will just see geometrically, you will have visualization which will also be projected, which you will be able to understand it here. So what are we going to do here? So what I am going to have is, assume that I am going to work with A 3 by 2, right. I am going to look at a matrix A 3 by 2. That means A is going to act upon A transforms X in Rn, X in Rn to B in Rm, where Rn here corresponds to R2 in this case, in this example, and Rm is basically R3 in this example. So what are we going to do? So A is going to transform a 2 component vector to a 3 component vector, and we want to see how is this happening, right. So we want to see how is this transformation getting effected, right. How is it getting effected? So what are we going to do? I am going to take A 3 by 2, I am going to say acts on X 2 by 1 is going to give me B 3 by 1, right. So basically you have Rn here, which is basically R2, and I have R3 here, which is basically, say I am going to take a vector here and then I am going there. So this is going to be my X vector, that is going to be my B vector, and I am going to act upon A by, I mean act on X using A and then get to B. Now let us study this on, as I said, I mean with the help of geometry we will be able to get it better. So what happens here is we have A is equal to U sigma V transpose X, I mean V transpose, this is what we have. So consider what I am going to do is I am just going to take a let us say I am going to take a unit circle here, I am going to take unit circle here, unit circle, assume that this is a circle, and okay, assume that this is a circle, right. And what am I going to do now? I am going to look at a point on this circle which is basically, let us say, this vector X. This point that I have is basically X. This is going to be in R2. Now what I want to do is I am going from here to, let us say, this. I have my x1 axis, x2 axis and x3 axis in R3. This is basically the x1 axis and x2 axis in R2. So, this is what we have. So, it is going to point me to some other vector. This the matrix A is going to take me here from here, and I am going to land up in some other vector, let us say B. This is what happens, and this is exactly what we are trying to capture in terms of our Ax equal to B, like what is it happening. So, what I do is I take this vector x, I am going to write this as Ax is equal to U sigma V transpose x. Now, what did we say? V transpose x, if you do V transpose x, V is basically a matrix, n by n matrix, it is going to take an n component vector, it is going to give me another n component vector, let us say W, and the length of W and length of x are going to be the same. So, what am I going to do? I am going to have this. So, the first step here is basically I have this unit circle on which I have this point x. Now, what I am going to do is this point, when I am going to act upon with my V transpose. So, the first step I am going to do is I am going to do V transpose x. Now, V transpose x is still going to be in R2. What am I going to get in R2? In R2 I am going to see this point x is going to get rotated to some other point, let us say W. So, this is where I am going to get, and the length is going to remain the same, right. Assume that these two circles are of the same length and unit circle we are talking about. Now, once V transpose x is done, then what happens? V transpose x is basically now going to be acted upon by the sigma matrix. Then the sigma matrix is basically m by n matrix with R non-zero scalars, which are basically the singular values, R non-zero singular values, where R is the rank of the matrix A, singular values. Now, you can take this V1 and V2, the matrix V, if you take it in R2, I mean it is going to be a 2 by 2 matrix. So, let us write that also. This is 3 by 3 matrix, this is a 3 by 2 matrix, and that is a 2 by 2 matrix. So, my V vectors are going to be something like this. I have this V vector, V1 vector, and let me say I have another vector, let us say let me put it this way. So, let me call this as my V1 V2 vector, let me call this as my V1 vector. So, V is going to have a 2 by 2 matrix and these two are the vectors. So, I am going to get W here. Now, what happens is after this gets basically stretched by, let us say this is of rank 2. So, I am going to get uneven stretching in two different directions in R3. Therefore, when you go to R3, what happens is geometrically it basically becomes an ellipse. So, you basically get some kind, you basically land in an ellipse where you have this axis and let us say you have this to be the axis. So, we have this to be the major axis, which is obtained by sigma 1 V1, and this is basically my sigma 1 V1, and let me say this is going to be my sigma 2 V2, right, where V1 and V2 are the eigenvectors, orthonormal eigenvectors which we had, and the sigma 3 is going to be 0 here. We are going to say a rank 2 matrix here. So, we will say A is rank 2, A is rank 2, right, A is rank 2 matrix. So, this is what is going to happen. So, after this step you go into third dimension, because this 3 by 2 matrix is going to transform this 2 component vector to a 3 component vector. So, I am going to get say some other vector which is going to be, let us say some p vector, what I have here, which is basically sigma V transpose x, that is going to give me my p vector. Now, what happens, this p vector is going to be, so this is basically sigma V transpose x, this is V transpose x, that is sigma V transpose x. Now, what happens, this p vector is now going to be again rotated by the u vector in the 3 dimensional space. So, what am I going to get? I am going to get something like this. So, I will have, okay, let me put it this way. Let me take it this way. So, this is the ellipse that I have. Now, what am I going to do? This point P is here and the point P is obtained as sigma V transpose x. Now, what we do from here? This is going to be UP vector, which is nothing but U sigma V transpose x. And what am I going to get? This U vector is going to act like a rotation transformation. So, what am I going to get? I am going to get something like this: x1 axis, x2 axis and x3 axis. This point P is going to get rotated to some other place. So, I have my, let me do this, okay. So, I am going to get something like this. Sorry for the bad illustrations, you will see it in visualization properly. So, you are going to get something like this. So, this is going to be my that sigma V2 vector, which is basically my U1 vector, and this is going to be my sigma V1 vector, which was basically the U1 vector, and the point P is going to get rotated to here, and this is going to be my B vector. So, the effect of the singular value decomposition is basically it is basically the if you look at the action ellipse, you see that it is going to be a few rotations and scaling followed by rotations, right, which is exactly like what we had there we called it as projections, here we are going to call it as rotations even, right. So, that is exactly what we have here. So, this is the geometrical meaning of singular value decomposition. Now, there is one more interpretation to this. You remember when we did our eigenvalue decomposition or eigen decomposition, when we did we got into this, we said Ax is equal to lambda 1 UU transpose x plus lambda 2 VV transpose x. If you look at this, this is basically a basis expansion for, this is a basis expansion for what do you call, you are going to write this A as a for the matrix A. A is a symmetric matrix, real symmetric matrix, and what are we writing, what are we doing? We are going to UU transpose is a symmetric matrix, VV transpose is a symmetric matrix. So, what are we writing? We are expressing A as a linear combination of real symmetric matrices UU transpose and VV transpose. The moment you change lambda 1 and lambda 2, the matrix A will change. Keeping keeping the vector u and v the same, you keep changing lambda 1 lambda 2, the matrix A will change, which means UU transpose and VV transpose act as basis vectors for the vector space of 2 by 2 real symmetric matrices. And what we have is A real symmetric matrix with distinct eigenvalues is now it now has a basis expansion in terms of this UU transpose and VV transpose. Now, what am I going to do? Can I get something similar to that in singular value decomposition also? Of course, what we have here is A is equal to U sigma V transpose. This is what we have. Now, if I write it this way, I will get this as, let us say, the U matrix is basically U1, U2, etc. UR, then I have UR plus 1, etc. to UM. Why we take it as UM? Because U is going to be an M by M matrix. This is an M by N matrix. So, U is an M by M matrix, this we already saw, and this is going to be okay, this is M by M, this is M by N, this is N by N. We have this, then we have sigma 1, sigma 2, etc. sigma r, and then everything else is going to be 0. This is going to be an M by N matrix, where this you have r columns here and this is going to be r rows here. So, you are going to have m minus r rows of 0, and then you have n minus r columns of let us say n minus r columns of zeros, then you have m minus r cross n minus r number of zeros here, right. So, this is what we have. And on the other hand, what is the third matrix that we have, which is nothing but V1 transpose, the first eigenvector. So, V1 transpose we have, V2 transpose, V3 transpose, you have etc. VR transpose, etc. VR transpose. Of course, we will take VR plus 1 etc. transpose to Vn transpose, we will put it this way, right, where V1, V2, Vr are all the eigenvectors of A transpose A, and Vr plus 1 to Vn, these are basically the eigenvectors corresponding to the 0 eigenvalue. So, basically we will say this is n by n matrix. Now, what we have here, so if you multiply this thing, so you will get this U matrix which is U1, U2 etc. Ur, then Ur plus 1 etc. Um, and what we get here, we are going to get here sigma 1 V1 transpose, sigma 2 V2 transpose etc. sigma r Vr transpose, the rest of the things is going to be 0, right, because it is going to get multiplied with this. So, rest of it is going to be 0. So, I have m by n, right, this is going to be m by m matrix, this is going to be let us say m by r matrix we have, right. Yeah. So, the rest of the things is all going to be 0 here. So, let us take this also to be okay, m by n matrix. So, we let us take this, we still have this m by m, let us come to this later. So, this is all going to be 0, right, because 0 is going to multiply each of those rows. So, the rest of it is all going to be 0. Now, what we have here, this is U1. So, this is going to be A is now going to be U1 sigma 1 V1 transpose plus U2 sigma 2 V2 transpose plus etc. plus UR sigma r Vr transpose, rest of it is all going to be 0. Now, if you see, this is a scalar, this is a scalar, this is a scalar, all these are the singular values of the matrix A. So, what am I going to do now? I am going to rewrite this as, sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose plus etc. plus sigma r UR Vr transpose. That is interesting. So, let me rewrite this again. So, I have A is equal to sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose plus etc. plus sigma r UR Vr transpose, where sigmas are all the, where let me write this, where sigma i's are the singular values of A, singular values of A, right. And we of course know what are V1, V1, U2, V2 etc. These are all the eigenvectors of A transpose and A transpose A. So, we already know that. Now, what we have here, this is, if you take U1 which is basically an m by 1 matrix, and V1 transpose is basically a 1 by n matrix, right. This is going to be a 1 by n matrix. So, what is U1 V1 transpose? This is the outer product of the two matrices, this is the outer product. You remember U transpose V was inner product, right, we defined this as the inner product of the matrix to the two vectors. Here we are going to look at the outer product of two vectors, outer product of two vectors. So, the inner product of two vectors resulted in a scalar, U transpose V was a scalar. Now, what is U1 V1 transpose? This is going to be an m by 1 matrix, which is m by 1 matrix, which is going to multiply with a 1 by n matrix. What are we going to get? We are going to get an m by n matrix. Oh, that is brilliant. Why? Because each of this is going to be an m by n matrix, and this fellow is an m by n matrix, A is an m by n matrix. So, what we have? We have sigma 1, this is an m by n matrix, this is an m by n matrix, and that is an m by n matrix. So, what are we seeing here? Oh, this is going to be, let us say, sigma 1 some m by n matrix plus sigma 2 some m by n matrix etc. sigma r m by n matrix, and these matrices have nothing in common. Therefore, these matrices U1 V1 transpose, you already know that U1 U2 U1 U2 UR are orthogonal to each other, V1 V2 VR are orthogonal to each other, and therefore, U1 V1 transpose, U2 V2 transpose, UR VR transpose will become linearly independent vectors in the vector space of m by n matrices. So, I'll write it as UI VI transpose is an m by n matrix and we will write this as U1 V1 transpose comma U2 V2 transpose comma etc. UR VR transpose form a basis for the set of all m by n real matrices. Right. Well, that's interesting now. So, now the moment you say it is the basis for the set of all m by n, the basis for the vector space of let me say vector space of all m by n real matrices, all I have seen is I am expressing this this matrix A as a basis expansion here, where the scalars are going to be the singular values themselves. The moment you change the singular values, the matrix changes, right. The basis, it is exactly what we had. If you remember the definition of basis, suppose you say U1 U2 UK are basis vectors, then alpha 1 U1 plus alpha 2 U2 plus alpha k UK will give me a vector which is, let us say, B. Now, what happens is, if I keep changing the scalars with the same set of vectors U1 U2 UK, I will end up getting different vectors B, right. That is exactly what happens here. I will retain U1 V1 transpose, U2 V2 transpose, UR VR transpose to be the same matrices, meaning U1 V1 transpose is one matrix, U2 V2 transpose is another matrix, UR VR transpose is another rectangular matrix. Now, if I change sigma 1, sigma 2 etc. sigma r, I will end up getting different values of A, which means I am just doing a basis expansion. So, singular value decomposition, if you see, is actually a basis expansion of the matrix A of rank R. Assume that this matrix has a rank R, matrix rank is R. Now, something interesting comes up. What is the rank of the matrix U1 V1 transpose? Let us look at that. U1 V1 transpose, assume that U1 is basically the vector, let us say what do we call, let us say 2 3, and V1 is a vector which is basically 1 4 5, let us take this. So, what is U1 V1 transpose? U1 V1 transpose is nothing but 2 3, right, into 1 4 5 is what we have. Now, what is this? You can multiply these two. So, this is a 2 by 1 matrix, this is a 1 by 3 matrix. So, the resultant is going to be a 2 by 3 matrix. If you look at this 2 by 3 matrix, this is going to be, the first column is going to be 2 by 2 3, second column is the 4 multiple of 2 3, which is basically 8 12. The third column of the matrix is going to be 5 multiple of this vector 2 3, which is going to be 10 15. Now, if you look at this matrix, the rank of this matrix is 1, rank is equal to 1. How do we say that? This is a multiple of this vector and this is also a multiple of this vector, therefore, there is only one linearly independent column in this matrix, therefore, the rank is 1. Therefore, you see U1 V1 transpose is a rank 1 matrix, rank 1 m by n matrix, right. Now, what we see here? We see the same thing here. I have A is equal to I will write it as summation, I is equal to 1 to R sigma I UI VI transpose, which is nothing but sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose plus etc. plus sigma R UR VR transpose. This is what we have. All of these guys are rank 1 matrices. The moment you see the outer product of two vectors will give only rank 1 matrices. So, let us write that outer product of two vectors outer product of two vectors u and v, two vectors u and v defined as uv transpose, results in m by n rank 1 matrix. So, what are we doing here? When you look at this, we are saying that A is basically a linear combination of R rank 1 matrices, linear combination of R rank 1 matrices. So, when you do SVD, you are actually trying to do a basis expansion for this real matrix A m by n in terms of rank 1 matrices. How many rank 1 matrices? R rank 1 matrices, where R is the rank of the matrix A. R is the rank of A. It is like saying I have, let us say, a 10 rupee note. Now what I say is I want to get it in terms of 1 rupee denomination. So how much I will get? I will get 10 1 rupee denomination. That is exactly what I get here. So A is being expressed as 10 1 rupee denomination here. So in terms of rank 1 matrices, and that is the intuition about SVD. First thing is SVD geometrically we saw here, and now what we have seen is SVD is also a basis expansion for real matrices of dimension m by n. Of course, you can do it in the SVD exists for all kind of matrices, square, flat, wide, fat, whatever, tall, every kind of matrix you have singular value decomposition, and that would actually be a basis expansion. This is another insight that we have got, which is exactly like what he had for real symmetric matrices, which was also a basis expansion, right. So, we understood SVD in the last class by Dr. Ashok Rao, and we also got some intuition about SVD now here, what is it doing geometrically and what is it as a basis expansion. In the next class you will look at support vector machines by Dr. Ashok Rao. Namaste.